Obviously, central to studying quadratic functions is to solve quadratic equations. So here's a general quadratic equation where the coefficient a is non-zero of x squared to ensure that it really is quadratic. Solutions to this equation are called the zeros, or sometimes called the roots of that function ax squared plus bx plus c. So if you're asked to solve an equation, it's the same thing as finding the zeros of the function, or the roots of the function, depending on the context. Very frequently, we're interested in real number solutions to that equation, and those correspond geometrically to the x-intercepts of the graph of y equal to the quadratic function. Anytime you find a solution, say x is equal to r, where r is a root or a zero of the function, that corresponds to a linear factor, x minus r, of the polynomial itself. Let's illustrate this with an example. Suppose I have the quadratic equation 2x squared plus 5x minus 3 is 0. If I can factor this into linear factors, then I can solve the equation. So I might just naively try to factor it visually. If I have 2x squared, I'm probably going to have for my first terms 2x and an x to get that 2x squared. I then need to choose some numbers to go in the last two terms whose product is minus 3. There's not many choices here if it's going to be a nice result. 3 and 1 would be one choice. You start to think about multiplying those together, and I have 2x and 3x, and that would give me 5x if I add them together. But the problem is that then 3 times 1 here doesn't get me minus 3, it just gives me plus 1. Or plus 3 rather. And so that can't be the right factorization. And so we try something else. And instead now I'm going to switch the 3 and the 1 around. And let's see if I have more luck here. So 2x squared. And I'm just going to make them both minus right now. That will be minus 6x, but I want plus 5x. So I feel like I should make this one plus to get plus 6x. And then minus 1 times x will take that away to get me positive 5x. Having this mismatch of signs is right because minus 1 times 3 gets me minus 3. And indeed, those are the right factors for this quadratic equation above, for the quadratic polynomial. And once I have that and I set them equal to 0, it must be that either this factor is 0 or this factor is 0 because I'm multiplying them together. So linear factors, 2x minus 1 has to be 0, or x plus 3 has to be equal to 0. I can now solve each one of them and find a root of this equation. First one tells me 2x is equal to 1, so x is equal to 1/2. And the second one tells me x is equal to minus 3. So we have two real solutions, and that means that this parabola, when I plot it, corresponding to this quadratic function, will have two x-intercepts. So we found both the solutions, the zeros, the roots of the equation. We see that two of them are real, so there's two x-intercepts, and we also see the linear factors initially as well. If I plot this, we'll see the two x-intercepts at minus 3 and at positive 1/2. This parabola is opening upwards according to that coefficient of 2, if that's what we're going to plot here. And so this is y equal to 2x squared plus 5 minus 3. And you can even plot the y-intercept down here at minus 3. So doing this problem really depended on being able to factor visually here, and notice there was a bit of trial and error involved. It could be that we just don't see all the options, or we miss it and we don't see how to factor it, or it just could be that the linear factors are not nice. It could be that the roots of the polynomial may not be simple numbers like 1/2 or minus 3. They may be irrational numbers. They may involve radicals, and they could be very unclear what their values are just by visually inspecting the equation. So in that case, if we really need to find the roots of an equation, a quadratic equation, we can always fall back on the quadratic formula. which has a wide range of applications in engineering. So it's really important for us to take some time to review this. So it says that if you want to find the solutions to a standard quadratic equation, you can express those solutions in terms of the coefficients a, b, and c. And it says that the solutions to this equation are x equal to minus b plus or minus the square root of b squared minus 4ac, and that entire quantity is divided by 2 times a, where a is non-zero necessarily, or it wasn't a quadratic equation to begin with. You should be familiar with this, and just being able to interpret this expression goes a long way to understanding how certain physical systems actually behave. It's quite remarkable how this familiar algebraic equation or expression here, formula, has a wide range of interesting interpretations. And the key thing is to look under the radical at b squared minus 4ac. The problem is that sometimes that could be negative depending on your coefficients, in which case you're not going to get real number solutions. So that expression under the square root is going to determine or discriminate between the different number of solutions and the kinds of solutions that you might get in a quadratic equation. And as such, it's called the discriminant. It's typically written as delta, and it's defined to be b squared minus 4ac. If delta is a positive number, that's great. I'm going to take the square root of a positive number. It will be something non-real here and non-zero, and then I'll add or subtract it to this expression here and get 2 different numbers. So in that case, if delta is greater than 0, the discriminant is greater than 0, then we'll get 2 distinct real number solutions to the quadratic equation. If delta is equal to 0, then it's 0 under the radical, and adding or subtracting 0 doesn't really change it, and we'll only get one solution. Of course, quadratic equations should have 2 solutions to them, so we call this a repeated real solution. We'll see 2 linear factors that are the same linear factor. It's a repeated solution or repeated root of the equation. And then if delta is less than 0, that means we'll see non-real solutions. They'll be complex numbers, but non-real numbers. And we'll talk about complex numbers in a little bit, and imaginary numbers to express those solutions. So let's look at an example. Let's take 4x squared minus 12x plus 9, set it equal to 0. Let's find the zeros of that function. And we're just going to go right to the quadratic equation. So a, b, and c are the coefficients. Make sure you include any sign as part of that coefficient, so minus 12 for b. And the solutions will be x equal to the opposite of b, so that's 12, plus or minus square root. I'll square b, it'll become positive 144, minus 4 times a, which is 4, times c, which is 9. And I divide that all by 2 times a, so 2 times 4. And let's simplify. Let's see what's happening under that radical. I have 144 minus 144. 4 times 4 is 16. 16 times 9 is 144. So under the radical we have 0. So our only solution is going to be 12 over 8. The discriminant is in fact equal to 0, and that's just telling us there's one but repeated real solution. That's 3/2. Delta was 0, so x equal to 3/2 is what we would call a repeated root of the equation. We could have just factored this visually above. If I go 4x squared, I'm probably going to have 2x and 2x. Could be some other arrangement, but let's try 2x and 2x. And then I need to pick something here whose product is 9, and I'm going to try 3 and 3. And if I just check it as is, 4x squared minus 6x minus another 6x gives me the minus 12x, and the signs are right to give me plus 9. So in fact, here's the two linear factors, and each of those linear factors has a root of x equal to 3/2. Here we see a repeated linear factor. It's 2x minus 3, all being squared. Graphically, this means we only have one x-intercept, and that's because the vertex of the parabola is just touching the x-axis. So here's the graph of 4x squared minus 12x plus 9. My coefficient 4 is greater than 0. It's going to open up. My single real root corresponds to the vertex just touching the x-axis, and there's the graph of the function.